Let's analyze identities to solve equations. Let's go back to geometry, the two-column proof. Let's do it. No, let's not do it. Let's just show a little bit of reasoning for each step that we do. In this video, we're going to focus on solving trig equations by using some of the identities that we're getting a little bit familiar with. We're not all the way there yet. That's totally understandable if you're still wrestling with a few of the identities and how to manipulate the expressions or equations. And so this is analytical trig, so we're getting analytical. Are you judging or analyzing my cursive? Is that a good Z? I always struggled a little bit with the Z's. Is that how you do the Q? Okay, here we go. Let's check out an example first off. Double check if you have an example that you're working with on your page that this is exactly how it's written there. May have made a mistake. But for anybody else, here's the example we're going to work through and simplify using the identities that we've used on a previous video in the first part of this lesson 1A. Alright, so some of the approaches that we're going to take to simplifying expressions and solving equations is quite varied. But for the most part, we're going to just use the algebraic techniques we know of already. So some of those include common denominators and difference of two squares, expanding, distributing, factoring, using fractions properly, so dividing fractions by fractions, meaning you're going to multiply by the reciprocal. And because we have reciprocal functions, we could use those in unique ways. We can approach them in different ways. So we have, for this expression, just so you know, we have 5 steps that we're going to take. So the first one, this expression is begging us to expand. So I'm going to call this an expand step. And what that has us do is just distribute using the FOIL method. And because it's a difference in two squares, we only have the first two terms multiplied, which is cosecant squared x, and the second two terms, the last terms being multiplied, which is minus 1. And we're going to divide that by cosine squared x. We're not going to do anything with that cosine squared x yet. Alright, so a pretty simple step. We just expand that expression. Now, I'll invite you into my brain right here. When I see cosecant squared x minus 1, I'm thinking, oh, that is a Pythagorean identity. Something is squared, so it's hinting at me to check out that identity. So we go back and we see, okay, I'm flipping to a page here, cosecant. Oh, that involves a cotangent, but it's not written the way that it's listed there. I actually need to manipulate it a little bit. So I subtract 1 from both sides, and I get cosecant squared theta, or x, minus 1 equals cotangent squared theta, or x. All right, so number 2, the reason for number 2 is a Pythagorean identity. Cosecant squared x minus 1 is cotangent squared x. And we're going to divide that by cosine squared x still. Not too bad so far. So 2 different things that we did there. One was algebraic and one was trigonometric. Now the third step that we're going to take is we're going to apply a quotient identity. Quote ID. And there are 2 ways that we could do this. Really, when we see cotangent squared x, we can rewrite that as cosine over sine squared x, and then rewrite cosine squared x if we wanted to, or leave it as it is. But because I don't really want to deal with fractions and fractions, what I'm going to do is rewrite the numerator using the quotient identity, which is cosine squared x over sine squared x. All right, so that's the second one, the quotient identity. And then I'm going to multiply that by 1 over cosine squared x. So I'm treading lightly here because I know that many students at this point, either in 10th grade or 11th grade, might be inclined to divide fractions by fractions. And so I'm saying here's an alternative method that we could do to avoid, writing these fractions and you have this vertical space here that we're trying to deal with. All right, so now you could see that you could actually simplify by crossing off these cosine squares. So it's a little bit more practical in that sense. So that 4th step I'm just going to call simplify. And maybe I'll cross that off in the previous step, but I think it's more powerful that if we say what we're doing and then write down the result. So 1 over sine squared x is the result of canceling those cosine squareds. Now you may be done. You may see an answer to this question and like, oh yeah, that's the answer. But usually we would rewrite that as a cosecant squared x, because we don't have any fractions. It's just simply that function. And the reason for that was a reciprocal identity. All right, so we had a reason for each step, and we showed each step without too much work there. So you could apply that to some of the other expressions that you're working with. And let's take a little bit of that and apply that to solving an equation. So this is the main event right here. This is the main thing in topic 1b, and some pretty challenging stuff arrives from this. So solve sine cubed x over cosine x equals tangent x on this specific interval. Now it gives us an interval because you know that these functions are periodic, so there could be multiple answers to this equation, multiple solutions, multiple x values or angles that make this equation true. So we need to limit that by saying we're going to include 0 and we're going to go on the interval from 0 to 2 pi, not including 2 pi. So if 2 pi ends up being an answer to this equation, we're going to not include that in our solution. And so we're finding all of the values. All right, so I'm not going to write down the actual reason for this because I'm trying to conserve or preserve space here. So I'm simply just going to write down the steps that I'm taking and then actually take them. So the first step is I'm going to convert tangent x to sine x over cosine x. And you may not know to do that, but really, if you think about it for a moment, we could break down any function in terms of sine and cosine, or do as best as we can to do that, so that we're only working with sine and cosine, and then we could use algebraic techniques like factoring and stuff like that. Now this doesn't apply to this particular equation here, but if we ever have an equation where we feel like we need to divide something, so if this was sine cubed times cosine, we don't want to divide by an entire function involving x, because there could be a solution in there that ends up working, and by dividing it, we're dividing out that solution. We're taking it out completely. All right, so now the next step is saying, oh, well, if we're dividing sine cubed x by cosine x, well, we can multiply by cosine x on both sides, so we end up getting sine cubed x equals sine x. So in this case, notice we're not dividing by cosine x. We're not taking out that solution. In fact, it could make our solutions even more populous, is a word? Is that a word, William? I don't know. We could check it out. Tristan probably knows. Let's continue. Oh, introducing Thought Bubble by Mr. Stark.
Nerd alert. Ladies and gentlemen, I believe this looks like something of the form, oh, I'm going to choose the variable here and just be careful with this. This looks like u cubed equals u. So that means this is initiating an informational approach to something I've learned previously in a pre-calculus or Algebra 2 class. That is of the fact of polynomials, the way that you would solve them is put them in the form everything on one side is equal to 0. Henceforth, you can factor out the polynomial in such a way that you can initiate what is called the zero product property. If a times b equals 0, then either a equals 0 or b equals 0.
This has been a Thought Bubble by Mr. Stark. Thank you for watching. Wild stuff, ladies and gentlemen. So we have sine cubed x minus sine x equals 0. Ooh, we're going to write quite a bit more here, just so you know. We're going to factor out that sine x, so we get sine squared x minus 1 equals 0. Oh, a common mistake students would say, if you factor out a sine x, you just get 0 over here instead of 1. There surely is a 1, and that will allow us to get the solutions we need. Okie dokie then. That means that, here goes, let's do something in red. Sine x equals 0, or sine squared x equals 1. All right, I just did a quick solving of this right one here for sine squared x equals 1. So now we have two equations that we're solving. Instead of one big equation, we have two smaller equations, sine x equals 0, sine squared x equals 1, which means that if you take the square root of both sides, you get sine x equals positive or negative 1. So I'd like to just pause for a moment to recognize this, the fact that sine x equals 0, when I think about 0 to 2 pi, I know there are multiple solutions. And when I think about sine x equals 1 or negative 1, I also know that there are multiple solutions. So the fact that these functions are equal to 0 or 1 or negative 1, that means I'm going to consider a sketch of the sine curve. If this is sine x equals 1/2 or root 3 over 2 or root 2 over 2 or something like that, then we know it's going to be a triangle that we're going to sketch. And you'll come across those in some of the exercises. Still good? All right, stick with me here. Here we go. Mary Mead's ready for these details. She's getting pumped. So now we have these two solutions, yes? Or these two equations, sine x equals 0, sine x equals positive or negative 1. So I'm breaking those down. I have a new setup, kind of a new train of thought here. Sine x equals 0. So I'm going to find those points. Hey, that's right there. The function is equal to 0. Hey, that's right there. And that's right there. So this value is pi. This is 2 pi, which is excluded. So even though it's a solution to this equation, it's not part of the original interval that we want. So we only have two solutions to the red equation, x equals 0 and pi. And now let's take a look at the green one. When is sine x equal to positive or negative 1? This is 1 up here. This is negative 1 down here. Okay, so now we have sine x equals 1, and that's pi over 2. Sine x equals negative 1. Notice I didn't sketch the actual points on the graph or the coordinate x-axis until I actually sketched the curve, because I just wanted to allow things to be flexible and get my sketch done quickly. All right, so that means that for the green curve, or for the green equation, x equals pi over 2 and 3 pi over 2. Phew, that was pretty challenging. But all stuff you know, you just have to piece it together and keep going. And if you're ever confused, you could sketch a triangle, sketch a sine curve, and use your calculator to support some things. Now, we have 4 solutions. There is one other thing that we need to double check. Remember that in the original equation, cosine x was in the denominator. And tangent x, when you think about it, cosine x is in the denominator there as well. So we need to basically check this equation that any of the x values that we found are not going to make that undefined. All right, so this is called finding the extraneous solutions here. The extraneous solutions. So going back to these solutions, if I plug in 0 and pi into the cosine curve, if I plug in 0, I get 1. If I plug in pi, I get negative 1. So those are fine. Now if I plug in pi over 2 and 3 pi over 2, I'll sketch a quick curve over here of cosine. Those values, make the cosine curve 0. So these solutions are extraneous. Oh, we did so much great work there. It's too bad they didn't make the cut. All right, so that is how you would solve an equation completely. And like I said, if you end up getting some other values other than 0 and 1s, you'll sketch triangles. Fantastic. Hey, thanks for learning with me and listening to my thought bubble there. Have a good one.